So after obtaining the 3D structures as well as the camera poses from the initial reconstruction as mentioned in the earlier slide, the next thing to do would be to apply bundle adjustment on these estimates to obtain a better 3D reconstruction. More specifically, we achieve this by minimizing the total reprojection errors, which we denote as delta Zij over here. And this can be illustrated using this particular figure over here. Suppose that we are looking at one particular image in the multi-view reconstruction as seen in the earlier slides, and we denote the camera matrix of this particular image as Pi. And suppose that there is a 3D point which is reconstructed and seen by this particular image, which we denote as xj over here. Its corresponding 2D points, which is the 2D point used to reconstruct this 3D point xj in the initialization step. Since we know that xj as well as pi over here, they are estimated from the algorithms such as the two-view geometry algorithm, PMP algorithm, and the linear triangulation algorithm. And this means that they contain uncertainty. And what it also means is that if we were to reproject this 3D point back onto the image using the 3D point itself, of course, and as well as the estimated camera pose, the reprojected point would not end up to be the same as the observed point xij over here. And there would be an error which is denoted by this delta zij over here, which is the Euclidean distance between the observed point xij and the reprojected point, let's call it x hat ij over here, that is being reprojected from this reprojection function over here. So the task over here in bundle adjustment would be to minimize this reprojection error over all the views as well as all the 3D points that is being reconstructed from the initial reconstruction. And we do this optimization over the camera poses as well as the 3D point. And mathematically, this can be expressed in this particular cost function over here. We do a arcmean over the camera projection matrices of all views and the 3D points that is being reconstructed from all the camera images. And by minimizing the square norm of this reprojection error that is given by xij, which is the 2D points that is observed in the image, minus away the corresponding 3D points that are reprojected onto the image over here. So pi over here represents the reprojection, where we compute this by simply multiplying pi and xj over here. We have seen this in the earlier lecture, but we shouldn't forget that this has to be normalized by the third element of the multiplication over here in order to make it a valid homogeneous coordinates of x, y, and 1 in the third element. W over here represents a measure error covariance that is used to weigh this particular error function over here. And now the cost function can be rewritten as a product of the error transpose multiplied by the weights and multiplied by the error itself. And this is a simple rewriting of the square norm equation over here, since everything inside this square norm is a vector. And here we can rewrite the error function into g of p, where p here is the variable to be optimized as written in the arcmean over here. And in the case of bundle adjustment, p would be a 12m by 3m vector because we have 12 parameters in the camera projection matrix, where we saw that it's actually a 3 by 4 matrix in the earlier lecture. This means that there are altogether 12 elements in here. And if we have n cameras, this means that altogether we have 12n camera parameters, as well as 3m point coordinates, where m is the number of points. 3 means that we have x, y, and z for each one of the points. We'll use the iterative estimation methods to optimize the cost function. Now, Let's rewrite the function in a more general way. Suppose that we are given a hypothesized nonlinear functional relation, which we call f of p over here. P here represents the parameters to be optimized, and x here would be our measurement vector. This is an n-dimensional measurement vector, where p here is the parameter vector that I've mentioned earlier on to be optimized in the Euclidean space. And let's assume that this has m dimension. Measured value of x approximating the true value uh, x bar is provided. So what this means is that we can measure the value of x that approximates a true value x denoted by x bar. And we wish to find the vector p hat that most satisfy this functional relation. So in the case of the bundle adjustment, x, the measured value of x, would be the image coordinate point that we have observed. And we want to find the vector p, which is all the parameters. In the case of bundle adjustment here, that would be equivalent to all the camera poses as well as all the 3D points from the initial reconstruction. And we want to find this particular vector over here that best satisfy this relation over here, x equals to f p hat minus epsilon, where epsilon is the error between x and fp. So we can rewrite this equation over here, this particular relation over here, into epsilon equals to f p hat minus x. And since f px is what we predicted from the parameters that we wish to optimize over, and x is a measurement vector that we have defined earlier on. What this means is that we want to minimize the error between what we have predicted and what we have observed, as denoted as epsilon. And we do this by defining another function, g of p hat, to be equals to the half of the norm square of this error function that we have defined earlier on here. And this can be rewritten into a vector form, where it's simply equivalent to half of epsilon transpose epsilon, where epsilon here is actually a vector that we obtain from these two guys over here. Now we'll look at 4 different methods to minimize the error function. And in particular, we'll look at the Newton's method, the Gauss-Newton method, the gradient descent, as well as the Levenberg-Marquardt algorithms. So we'll start by looking at the Newton's method, and this requires us to define what is known as the Hessian matrix. So suppose that we let P0 be the initial estimated value. So recall that earlier on in this slide, we denote P as our parameter vector that we wish to optimize over. Now let's let P0 over here be the initial estimated value, and this means that we would have an error of g of P0. We may expand this g of p, the function, which this is actually the error function that we have defined earlier on. And since this is a nonlinear function with respect to p, we can linearize it using the Taylor series to get this function over here. So we will just use the operating point of which is the initial estimate p0 plus delta. This means that there is a delta change in the parameter p0, and it would be equals to g that is defined at p0 plus the first order derivative of the function g with respect to p multiplied by delta. Delta is the small change of p0 over here, plus the transpose of delta multiplied by the second order derivative of the function g multiplied by delta divided by 2. And there are many smaller order terms over here that we can ignore, where here more specifically the first order derivative noted by gp over here is given by del g over del p expressed at the point of p equals to p0. Similarly, for the second order derivative of the function g, it would be del square g over del p square, expressed at the point p equals to p0. The first order and the second order derivatives, they are called the Jacobian and the Hessian matrix respectively. Now suppose that we have a function fx which maps an n-dimensional vector into an m-dimensional vector, and we further assume that the first and second order derivatives exist on the n-dimensional space, then the Jacobian matrix is given by a m by n matrix of this particular form over here. So what we do here is that it takes in an n-dimensional vector and outputs an m-dimensional vector. What we will do here is that we will take f and simply take the partial differentiation of f, which is an m-dimensional vector, partially differentiate it by every single entries of the input. So there will be altogether n columns over here, and there would be m number of rows simply because the output of f is a m-dimensional vector. So we are going to take this whole column over here with respect to the partial differentiation of this column here with respect to the first variable, the first entry in the variable over here, x1. And this would form the first column of the Jacobian matrix. We can also simply denote the Jacobian matrix as Jij, which in short will be del Fi over del Xj. Similarly, for the Hessian matrix, it's going to be a n by m matrix in this particular form over here. So what we will do here is that we will take the second order derivative of the function f with respect to every single entry in the this x vector over here, and we'll subsequently we will do a partial differentiation with respect to every I and j coordinate of the x vector over here. So it will be del square f over del x1 square, del square f over del x1, and then multiply by del x2, and so on and so forth until we get del square f over del xn multiplied by del x1 square. Or in short, we can write every entry in the Hessian matrix Hij, it will be equal to del square of f over del xi and del xj. Now after the Taylor series expansion, we seek a point g of p1, where p1 is the new vector that we estimate, such that we minimize this function over here, g of p1, where p1 equals to p0 plus a delta change in it. We'll do the same thing. We saw earlier on that p1, since it's equals to p0 plus delta over here, we can expand this using the Taylor series expansion, which will give us this particular equation over here, where G0 is evaluated on P0, and GP is the first order derivative, which is also the Jacobian of G, and GPP is the second order derivative of G, and that's also the Hessian matrix of G. And we'll seek the minimization of this particular function over here with respect to delta. So in order to achieve this, we differentiate this Taylor series expansion over here with respect to delta and set it to 0 to get this function over here. So we can see that if we take this del g p1 over del delta, because this is independent of delta, this will go to 0. And this term over here is also independent of delta. We take this over del delta. This is going to be 0 as well. And this guy will become g of p, since it's a function of delta. And this is a square function of delta. So this would become gpp multiplied by delta. And the whole thing would be equals to 0, which is this equation over here. We can shift gp over to the other side of the function to get this particular equation over here. And we can see that this equation that we have obtained earlier on is an inhomogeneous linear equation that is equivalent to ax equals to b, where we can solve for delta using the pseudo inverse or the inverse of GPP over here. So once we have obtained delta, we'll do an update of the vector p in the next step by simply adding delta that we have found from this step to the p vector in this particular step. And we'll do this successively until convergence. So a remark about the Newton's method and using the Hessian is that intuitively what this method is trying to do can be visualized by here, where suppose that we look the variable that we wish to optimize for. Let's denote it as a one-dimensional scalar value p, and this is our cost function g of p over here. So what this Newton method is trying to do would be at every operating point. Suppose that this is my first p0 over here. What it's trying to do in this step is that it's trying to uh, approximate this particular point over here of this cost function using the quadratic curve over here, and then it's optimizing in that direction of this quadratic curve to get the minima over here. And so since this is the point at the minima, this would be the next P1 that we are looking for. And here it will approximate another quadratic curve on this particular operating point P1, and then you will move to the next minima over here. And so this will be done successively until we finally reach the local minima, which is shown in this particular curve over here. So what this means is that since Newton iteration is based on approximating a quadratic curve near the operating point, it's going to work best when this particular estimate P is already close to the optimal point. It's also further based on the assumption that the optimal point is quadratic. So once it's quadratic, it's going to converge very fast towards the local minima. And but this particular assumption might be invalid, especially when we are very far away, when P0 is very, very far away from the local minima. So at the very far away point, this might not be well approximated by a quadratic function, and hence the convergence would be very slow at the beginning. And another disadvantage of the Newton's iteration method would be that the computation of the Hessian matrix is difficult because it involves the second order derivative of the nonlinear function that we are interested in. So a way to mitigate the computation complexity that arose from the Hessian matrix would be to use the Gauss-Newton method. We have seen earlier on that since this function g of p represents the square norm error of the cost function that we now denote as epsilon bracket of p. So to denote that this epsilon over here is actually a function of p. We have seen earlier on that this is nothing but just x minus f of p, where f is the nonlinear function that we are interested in looking at. We also further seen that this square norm can be rewritten into a vector multiplication, a dot product given by this particular equation over here. We'll add a half over here for the convenience when we differentiate this to the square over here. And this, the first order derivative, which is del g over del p over here, given by this guy over here, gp, is equals to the first order derivative of epsilon transpose multiplied by epsilon. I won't go through the exact way of computing this because this simply follows the chain rule of differentiation, which you should know by now. And where epsilon here, epsilon p over here is the first order derivative of the function f that we have defined earlier on here. We can see this way that the differentiation of del epsilon over del p is simply equals to the differentiation of x f of p divided by del p over here. Since x over here is independent of p, it becomes 0. So all we are left with will be del f p over del p, which is given by this guy over here. And this is nothing but the Jacobian of this nonlinear function f that we have defined over here. And in the bundle adjustment case, not to forget, this nonlinear function is simply referring to the reprojection function, which we denote as pi earlier on. And we do this similarly for the second order derivative. So this would be del square of g divided by del p square. We denote this as GPP, and by applying the chain rule of differentiation, we'll get this particular term over here, where epsilon pp over here would be equals to the del square epsilon, the second order derivative of epsilon, which is equals to del square epsilon divided by del p square over here. And since this term involves a second order derivatives, and it might be very inconvenient or computationally expensive to obtain this particular second order derivative, bearing in mind that this is only part of one iteration in the whole iterative optimization technique that we are talking about. So what this means is that if we were to compute the second order differentiation, we have to do it many times over the X number of iterations that we have in the technique before it converges. So and this can incur a large amount of computational time. So in order to mitigate this computational complexity, we'll simply ignore this higher order term. And since we ignore this, we can write GPP, the second order derivatives, which is the Hessian matrix that we have saw earlier on, as epsilon p transpose multiplied by epsilon p. And this is simply equivalent to J transpose J, since epsilon p, as we have seen earlier on, equals to the Jacobian of the nonlinear function f over here. So what this means is that we now can approximate the Hessian matrix, which it was computationally expensive to compute with the product of the Jacobian matrix over here. And this would be much easier to compute, since we only need to compute the Jacobian once. After substituting the second order derivative of G, which is the Hessian matrix of G, as equals to J transpose of J, here we'll obtain this particular equation, J transpose J delta equals to minus J transpose epsilon. J transpose epsilon is equals to the first order derivative of the nonlinear function GP. And this equation over here would also be known as the normal equation. So we can also derive the same weighted iteration of the normal equation by adding the covariance matrix over here. So this is the final normal equation that we get if we consider the error covariance on both sides. You should work this out by yourself by adding error covariance here. So in this particular error function over here. So what this means is that we will end up with a equation of epsilon p transpose sigma epsilon p divided by 2. And if we start off from here by doing the first order derivative and the second order derivative and ignoring the higher order terms here, we will end up with this particular normal equation over here, where sigma over here, it's our error covariance of the measurement, x, and it is a symmetrical and positive semi-definite metric. So what this means is that J transpose J would be symmetrical and positive definite, since it's a metric multiplied by itself. And if sigma x over here, or if sigma, the error covariance x over here, is symmetrical and positive definite, it also means that the product of this would also be a symmetrical positive definite metric. And this would guarantee us to be able to flip this guy over here, because we can view this as a x equals to b. So in order to solve for x, we need to be able to solve for the inverse of a. And since this guy over here, which is equivalent to the A matrix, is symmetric and positive definite, this means that we can always compute the inverse of this guy to get x, which is delta over here. So once we get delta, we'll bring it back to update the p vector that we are interested in. So pi plus 1 would be equals to pi plus delta I in every iteration. And we'll continue to do this until convergence. Another way to compute the optimization would be to use what we call the gradient descent method. So in gradient descent, it's a very straightforward method. Instead of computing the Hessian matrix as well as the first order derivative, the Jacobian matrix, will simply compute gradient of the error function denoted by GP over here. And that would be given by epsilon P transpose epsilon, which we have seen earlier on in this slide over here. And we'll use this particular gradient to do what we call the gradient descent towards the local minima. So we can think of it this way, that we have a error function g of p over here, and let's look at a one-dimensional space problem where the variable to be optimized over is simply a scalar value of p. Now, as we have seen earlier on, that in the case of the Newton optimization technique, we would have to start from P0, an initial point, an operating point, and approximate this with a quadratic curve. And then the optimization will move towards the minima of this quadratic curve. And that will give us the next point P1. And we'll start the iteration here, taking P1 as the operating point, and do a successive approximation at P1. And then we'll do the same thing to descend to the minima, and we'll get P2, which is this point, and we'll do this until we reach the minima point. So gradient descent would be to do this thing without a quadratic approximation, but instead we'll do it directly by computing the gradient. So let's look at this one-dimensional space, and this is GP over here. If this is our cost function, what it's going to do is that at every point starting from P0 over here, we're going to compute the gradient at this curve over here. And then we are going to move in the direction of the gradient, which is given by this guy over here. We are going to scale this gradient using lambda, a hyperparameter that we define, and we're going to take a step in the negative gradient direction. This means that we are going towards the minima point, and then we'll take that point as the next P1, and successively we'll compute the gradient and take the negative over this particular control hyperparameter to control the step, and then we'll successively move towards the new point and successively compute this particular gradient that will eventually bring us to a local minima. Now, in comparison with the Gauss-Newton as well as the Newton technique, this gradient descent is definitely much easier to compute because we just simply compute the first order derivative and move into the negative direction of the first order derivative, which is the gradient of the error function. And gradient descent itself is actually not a very good minimization technique. The reason is because we are computing the direction of the movement with respect to the gradient, because the cost function that we have might be locally not smooth. So what this means is that by computing the gradient, we might be moving in many zigzag direction before we reach the optimal point. And this means that it's going to lead to a slow convergence. But in comparison to the Gauss-Newton or the Newton technique, gradient descent still can work reasonably well when it is far away from the local minima. And we will see how Levenberg-Marquardt algorithm combines the two techniques, the Gauss-Newton technique as well as the gradient descent technique, such that it gets the best out of the two worlds. So more specifically, the Levenberg-Marquardt algorithm is a slight variation of the Gauss-Newton iteration technique. We'll start by looking at the normal equation over here, which is the equation that we have derived when we look at the Gauss-Newton iteration method. And in Levenberg-Marquardt, we simply augment the J transpose J over here, the Hessian matrix, with lambda multiplied by I. So what this means is that suppose that I is a n by n matrix, we'll get a diagonal of lambda in here, in this particular matrix over here. And we iteratively refine, or we iteratively update the lambda parameter here over the successive iterations in the Levenberg-Marquardt algorithm. A typical value of lambda would be initialized to 10 to the power of minus 3 times of the average values of the diagonal elements in J transpose J. So what this means is that after we compute J transpose J, we get suppose m by n matrix. We'll take the sum of all the diagonal values and divide it by the total number of entries, which is going to be n over here. And to get this particular value, and we'll take 10 to the power of minus 3 multiplied by the average values of this diagonal of this Hessian matrix over here to be the initial value of lambda. And after we have computed this delta over here from the normal equation, J transpose J delta equals to minus J transpose epsilon over here. So we'll use this delta that is computed from the normal equation to update the value of P, where P here is equals to the previous value of P plus the delta value. And finally, once we computed the updated P, we'll use this updated P to compute the new error over here. Because epsilon is a function of P, which is given by the measurement minus away the nonlinear function taking in the newly updated value of P. And we can compare whether the error value over here is reduced or increased compared to the previous step. So in the case where there's a reduction of the error, epsilon over here, we will divide lambda by typically a factor of 10 before the next iteration, and we will also accept this new value of P that is estimated from the computed lambda. On the other hand, if this lambda over here leads to an increase of the error, then the increment would be rejected. This means that the newly computed P value will be discarded, and we will take the P value at this particular iteration to be the same as the P value in the previous iteration, and lambda over here would be multiplied by the same factor, and the augmented normal equations are solved again. So we'll see why do we do this adaptive changes to the parameter of lambda. When lambda is very small, the method is simply equivalent or essentially equivalent to Gauss-Newton iteration. We can see this from the normal equation in the Levenberg-Marquardt algorithm, when lambda here is very small. So this term over here becomes negligible, and we will simply get the normal equations that we have seen earlier on in the Gauss-Newton algorithm. And this means that what this means is that since we saw that when lambda is small, this means that there is a reduction of the error, because we see that when there is a reduction of the error, we are going to divide lambda by a factor, which means that we are going to make this lambda smaller. And as a result, we are going to turn Levenberg-Marquardt algorithm to be the same as the Gauss-Newton algorithm when there is a reduction of error. And what this means is that because we know that if there's a reduction of error in the cost function, we are probably already getting closer to the local minima. And as mentioned earlier on, when we are close to local minima, Gauss-Newton will work very well, because the local minima, we are here on the assumption that the local minima, it's getting more and more quadratic. And so hence Gauss-Newton algorithm will work best in this situation, and you will also converge faster at this particular situation over here. Hence, when there's a decrement in the error, we will make lambda small, and we will turn Levenberg-Marquardt algorithm into a Gauss-Newton algorithm that ensures fast convergence. So on the other hand, when lambda is large, what this means is that we have defined earlier on that there's an increase in error. When we saw that there's an increase in error, we want to make lambda large, because we are going to multiply a factor of 10 typically. So we are going to make it large. When lambda here is large in this particular normal equation over here in the Levenberg-Marquardt algorithm, when lambda is large, this term over here is going to outweigh J transpose J. And we can see that when this term over here outweighs J transpose J, then the normal equation simply becomes lambda multiplied by delta equals to J transpose of epsilon. And this is what we have seen earlier on as the gradient step for the gradient descent technique. And so what this means is that when there is an increase in error, we want to make the normal equation close to the gradient descent algorithm, which is a sensible thing to do, because as mentioned earlier on, when the estimate is very far away from the local minima, the Gauss-Newton technique is not going to work well, because when it's very far away, the chance is that it's likely not going to be quadratic at all. So Gauss-Newton is not going to work well in this case over here. But when it is far away from the local minima, gradient descent method will still work. It's except for it might be moving in a zigzag direction. But in this particular case, it's better for the algorithm to move in a zigzag direction than not to converge at all. So in this particular case, we will simply increase lambda and turn it into a gradient descent technique. So in other words, the Levenberg-Marquardt algorithm, it switches between the Gauss-Newton iteration and the gradient descent approach depending on the error that is being computed at this particular iteration. So indeed, we saw that when lambda becomes increasingly large, the length of the increment step decreases and eventually will lead to the decrease of the cost function.